This video is the third and the last video on analog communication, and it is based on the noise in analog communication systems. We summarize here the contents of this video. We know that the noise is unwanted signal that affects wanted signal. Source of noise and types of noise are discussed here. Thermal noise is also called Johnson noise or white noise, is an important noise source. Short noise is another type of noise which is present in systems. Noise level is determined by signal to noise ratio. Noise figure is one of the important parameters, and it is defined as a ratio of signal to noise ratio at input to output. Noise figure or noise factor can be determined for several cascaded amplifiers. Only first two stages are significant in determining performance, and Frisk formula is useful here for giving the noise figure or noise factor. Effect of noise on all on AM systems shows that AM systems, both DSP and SSB, have unity figure of merit gamma, so they do not provide any signal to noise ratio improvement over baseband communication systems. Figure of merit of the conventional AM is less than the baseband system, and the effect of noise is independent of frequency for phase modulated systems. For FM systems, effect of noise is more at higher frequencies as compared to low frequencies. In both phase modulated systems and frequency modulated systems, output signal to noise ratio is proportional to the square of modulation index beta. Increasing beta will increase the bandwidth requirement, that is, signal to noise ratio is increased by increasing the bandwidth. Frequency modulated systems are more susceptible to noise threshold as compared to amplitude modulated systems. Threshold improvement is obtained by pre-emphasis and de-emphasis. So we have this noise analog communication systems, and we say it's analog communication part 3. So we start the presentation here. We know that noise analog communication systems is basically noise and unwanted signal, and noise is a random, and it does exist in communication systems. Basically, noise is broadly classified as internal noise or the external noise. Internal noise is the noise that is given by, or that is due to the active and passive components in the circuit, and external noise is external to the circuit. It's not internal to circuit. Internal noise due to random movement of the electrons in the electronic circuits. Major sources are resistances, diodes, transistors. Thermal noise or Johnson noise and short noise are examples of these internal noise. External noise, a man-made noise and natural sources over which we have no control, and examples are motors, generator, atmospheric sources, and many other sources, the external sources of noise. Noise level is in a system is proportional to temperature and the bandwidth. Also, it is proportional to the amount of current, gain of the circuit, and resistance of the circuits. These are the factors which were responsible for the noise. Effect of noise, it degrades the performance of the system. So both analog and digital systems, receiver basically cannot distinguish signal from noise, and efficiency of the communication system would reduce if there is a more noise in the systems. Types of noise, we said it's a thermal noise, which is also called a white noise, also called the Johnson noise, or again it's also called the fluctuation noise. The other noise is a short noise. The next is noise temperature as one of the parameter, and then the quantization noise. So these are the various parameters. Now we start with the thermal noise. Thermal noise is basically generated by the Brownian movement of the electrons inside the resistor, and this noise is zero at absolute 0 degree Kelvin, and generated when the temperature rise is, and we call it a thermal noise, also a Johnson noise. Sometimes this also is referred as the white noise, since it has uniform spectral density across the electromagnetic spectrum. Part spectral density of the thermal noise, SNF, is given as kT over 2, where K is the Boltzmann constant and T is the temperature in degree Kelvin, and kT is denoted by N0 sometimes, and then noise spectral density is N0 by 2. And here we have shown the plot for noise spectral density. This is the path spectrum for white noise or white process. Its noise is uniform R over for all the frequencies. Now path spectrum for thermal noise is identical to the white noise, only just towards the end there are some sags here. Now we observe that how this noise is represented. This work of Johnson and Nyquist has given an expression for the noise power. Noise power is mean square voltage. Here it's given by 4 kTBR volts. This is the noise power, where K is the Boltzmann constant, well-known constant, absolute temperature in kelvins, B is the bandwidth in hertz, and R the resistance in ohms. And here Vn is the mean noise, not power. Vn is the mean noise voltage. Vn bar is the mean noise voltage. It's not power, it's a voltage. Voltage here, the mean noise voltage. Now short noise is an electronic noise that occurs when there are finite number of particles that carry energy, and such as electrons or photons are there, so they give rise to short noise. And why it is said to be a short noise? Due to the analogy of the lead shots, is said to be like a short noise. It has again a uniform spectral density like thermal noise. Now we would try to see that how the performance parameters are given for the systems having noise. One is determination of noise level. Normally we determine the noise level as signal to noise ratio, SNR. We call it a SNR, signal to noise ratio, that's power of useful signal voltage, and divided by power of noise voltage. This is one way for representing. This is SNR as signal to noise ratio. The other parameter is noise figure. Noise figure is given as signal to noise ratio at the input to to power of noise voltage, basically not power of noise voltage, signal to noise ratio at the output. This is also the power signal to noise ratio at the output here. So SI over Ni over S0 over N0, and so in this case the noise figure is greater than 1. Okay. Now equivalent noise temperature is actually noise temperature is also, we represent noise measure as noise temperature. Actually it's not a physical temperature of any amplifier, but it's a theoretical construct that is equivalent temperature that produces that amount of noise power. So this is equivalent temperature that produces the same amount of noise power. T is temperature in degree Kelvin and F is the noise factor or noise figure. So we can determine the effective noise temperature. Okay. We can determine the noise figure of cascaded stages. There is a formula which is the Friss formula, and this calculates the total noise factor or noise figure for several cascaded amplifier stages. So this is given by F equals F1 plus F2 minus F1 over G1 plus F3 minus F1 plus G1 G2. So F is the total noise figure. This is the noise figure of the first stage, noise figure of the second stage divided by F2 minus 1 over G1 gain of the first stage plus F3 minus F1 over G1 G2 and so on. So what we notice here, because of this product here G1 G2, only these two terms are important in determining the overall noise figure. Okay, noise figure is mainly dominated by the first two stages, so that is what it indicates. So if you want to have a lower noise figure, you should be more concerned with the reducing the noise figures for the initial stages, that's first and second stages. Effect of noise on AM systems. Now we would see how this noise affects the amplitude modulated system. The channel we know that introduces additive noise in message, and this message received becomes corrupted, and a figure of merit, we define a figure of merit in this case, and this is signal noise ratio at the output over signal noise ratio at the input. Modulation systems with higher gamma has a better noise performance, and total noise is given by noise power spectral density into the bandwidth. And for the noise we have seen it was N0 by 2 into W will give me the total noise. And noise amplitude is having Gaussian distribution. It's assumed the noise is modeled as a Gaussian distribution, and that is additive white Gaussian noise, AWGN. This is the normal model which is considered for a noise. Now next is for AM suppressed carrier. We know for both DSP and SSP systems gamma turns out to be 1, and the signal to noise ratio at the input and output of detector are identical. There is no improvement in signal to noise ratio. For conventional AM using envelope detector, it comes, the gamma is 1 by 3 for amplitude modulation index of 1, that's mu is equal to 1, and the maximum value of gamma is 1 by 3 for the modulation index of unity. So it is even worse than the noise of a baseband system, baseband transmission system. Now noise and angle modulated systems like AM, noise performance of angle modulation is characterized by parameter gamma, and gamma FM is 3 by 2 beta squared, and it is compared with AM. If we compare this gamma FM over gamma AM, we find half of omega FM over omega AM, whole squared. And we note here, if the bandwidth ratio is increased by a factor of 2 here, that omega fm over omega am increased by a factor of 2, increase of a factor of 4 takes place in the ratio gamma, improvement of gamma fm over gamma mm. So it is increases by a factor of 4. This exchange of bandwidth and noise performance is an important factor of an FM system. That means the advantage of FM system is, if you increase the bandwidth, you can reduce the noise. You can improve the noise performance by increasing the bandwidth. Okay, so that is possible with the FM systems, which is not possible otherwise, like with AM systems. FM threshold effects, very important effect in FM systems where signal is well above noise ratio, and demodulated signal noise ratio, they are related by signal noise ratio is 3 beta squared C by n. This is the carrier's noise ratio, the signal noise ratio at the output of demodulator, and this is beta modulation index and carrier to noise ratio at the input of demodulator. So this not apply when SYN decreases below a certain point called threshold. So we notice here, next figure will show that below the threshold point this relation does not apply. So let us see this. This is the threshold curve for output SNR and carrier to noise ratio, and this is the region where there is improvement, if improvement region where improvement takes place, but this is a threshold point. At below this point this improvement does not exist. So the FM threshold is very prominent with frequency modulated systems, while it is not there are very less in amplitude modulated systems. Threshold improvement can be obtained by pre-emphasis and de-emphasis. Pre-emphasis is the we improve the signal noise ratio by increasing the magnitude of the high frequency signal with respect to lower frequency signals. That means a simple high pass filter can serve as a transmitter's pre-emphasis circuit. De-emphasis is the inverse process, where we improve the signal noise ratio by decreasing the magnitude of the high frequency signals with respect to the lower frequency signals. And a simple low pass filter can operate as de-emphasis circuit. The combined effect of these circuits is to increase signal noise ratio for high frequency components during transmission, so that they are not masked by noise. Basically this is very important method to improve the performance of frequency modulated systems, that is pre-emphasis and de-emphasis, and it's being used. Now here it's probably the last slide. This is indicating the type of filters used. That's a transmitter filter which is used here, and this is basically a pre-emphasis filter. Basically it's a high pass kind of filter here with the transfer characteristic as shown here, and the receiver filter is a low pass filter and having the RC component with the transfer function as shown here. So what we observe here, that noise is quite important for modulation systems, and the communication systems are being observed that how their performance is superior or inferior with the systems is one very important parameter is signal noise ratio here, and in the analog systems, and while in the for the digital systems we have bit error rate, so that is also related to noise performance of the systems. Okay, now I stop here and end of the slide. Thank you very much.